I've showed you already how this instrument looked like on top of the INT telescope. And if you don't remember, you could go back to section 6 just to check it out. But when the instrument is not placed on top of the telescope, like you're seeing here, you can actually open it and you can see where the CCDs are within the instrument. This is the wide field camera. Now these CCDs, the ones that are used for science, are this one, this one, this one, and this one. There's another CCD here that is actually used as an auto-guider cam to make sure that the telescope is pointing at the right place and that there's also no shift to do with tracking the movement of the Earth, because this tracking needs to be really, really accurate. And when you put this instrument on top of the INT, for example, at the prime focus to get a wide field of view, this is what this instrument specializes in. You can actually expose, and after one exposure, you'll be able to see something like this. And this is how the raw data will look like. It will actually give you 4 different images. In this case, I just combine them all together, but you'll be able to map this to the reality of the detectors. And you can see this is CCD number 1, this is CCD number 4 that contains this globular cluster that's in the center, CCD number 3, CCD number 2, and also the fact that there is no CCD here, so you don't gather any information. And again, this CCD is just being used to track the position of the telescope on the sky, and therefore it doesn't produce any real data. You can point the telescope at other things, such as, for example, Orion, that you can see right here. And you can also produce RGB images by taking images with this detector, but in front of it, you can put an R-band filter, then a blue band filter, a green band filter, and then you take actually 3 images per CCD. After you reduce them, you can produce a false RGB image like this. And this is how they are produced. But in this case, you can still see the pattern, and you can still see the small gaps actually between CCDs. This is just a physical consequence of the fact that CCDs will not be able to fully overlap. But if you want to produce an image that does not have any gaps like this, all you have to do is you take multiple images where you're moving your telescope up, down, and left and right, and you can easily feel those gaps. Because CCDs suffer from dark current, essentially counts are generated at room temperature, we usually always cool down the CCDs down to at least liquid nitrogen temperature, something like 70 Kelvin. You can see me actually waiting for the cryostat to be filled with liquid nitrogen. I was just sitting back with helmets and full protection as I was filling it with liquid nitrogen. And for instruments like this, you need to fill it back up every 12 hours to make sure that the CCDs never warm up and that the dark current is kept essentially to 0. However, even though cooling down CCDs to 70 Kelvin will get you the dark current to essentially 0, the readout noise is still significant. And for that, what we do is we make the detector just read itself without ever doing any exposure. Essentially a 0-second exposure, and we measure how many electrons we get per pixel. And after doing a few, we can get some statistical median and actually remove that level of electrons. That is because when we take a real exposure, that level of electrons will always be there, and they have nothing to do with the actual flux coming from the sky. One thing to point out is that even though CCDs always had really high quantum efficiencies, as time went on, actually the developments meant that they are becoming more and more red sensitive. This means that even at around 1 micron, CCDs, the red sensitive ones, are now really, really sensitive, and they can actually compete with near-infrared detectors. The other important thing to point out is that on top of CCDs becoming even more sensitive, especially towards the red, we can actually pile them up, not just 4, but something like more than 100. And you're looking here at the largest CCD camera. This is IPER Supreme Cam with a field of view that would capture many times the full moon, and that is placed on an 8-meter telescope. So it's incredibly powerful. And I would also challenge you to actually pause the video and try to count these CCDs, and you should be able to find 104. We also have access to detectors at longer wavelengths, for example, in the near-infrared, even though they're not technically CCDs. Near-infrared detectors, which are made of different components, are typically only sensitive in the near-infrared. So they'll not be able to capture any of the optical photon. And if you want a real example, this is how one of them looks like. This is VERCAM on the UK-built 4-meter VISTA telescope, made of 16 of these detectors. They're not CCDs, but we then use them in the same way. And you'll notice that in this case, the gaps between detectors are actually even larger. And for you to produce sort of a continuous image, then with this instrument, you would have to actually just follow an observing pattern to completely fill in the gaps. Now that we introduced CCDs and even near-infrared detectors, even though for near-infrared detectors, we will not be discussing them any further, apart from the fact that you can still measure their quantum efficiency. Now let's say that we have access to 3 different telescopes that you can see above, with also 3 different detectors with different quantum efficiencies at different wavelengths. Let's say that we want to calculate the effective areas of each combination at the different wavelengths to try to know which one is best for, say, 500 nanometers, which one is best for 900 nanometers, and also discuss a little bit about what would happen to our answers if we were actually to take into account the costs. Now, if we want to calculate the effective area, we don't just care about the area of the telescope, but in practice, what we want is to multiply the area of the telescope, so sort of d squared, by the quantum efficiency, and then calculate this effective area for each combination. If we do these calculations, then we realize that the most efficient option for 500 nanometers would be the VLT, because it gives you a very large effective area, and also the quantum efficiency for that specific instrument is very high. So you get an effective area of 51.2 square meters. On the other hand, you will notice that at 990, even though the efficiency of your detector here on keck is only 0.3, the quantum efficiency, because the area of keck is so high, this would give you the highest effective area. But of course, if we take into account the costs, we may actually conclude that this option, VISTA telescope, that's way, way cheaper with a relatively good quantum efficiency at this wavelength, could actually be suitable.